Okay, so we're recording now. Sorry to miss those quiz review questions. Okay, so another question was, could we review when the midterm will appear, open, and where it will be found? And yes, after hoping for a better option, but deciding that the risk of technical problems were probably insurmountable, at least for this first one. Where it's going to be essentially like these quizzes. So it's going to be on Canvas. It'll be the same, like taking a quiz, but it'll be longer. And there will be essay questions integrated into them. So that will be the main difference. Hopefully we don't have any problems with images and whatnot. I think I've figured out most of the problems we've been having because of these quizzes. So that part's good, at least. Yeah, so it will be visible as soon as I manage to complete it. Probably be tomorrow sometime. It'll be available to take during the course period. And for those who have extra exam time from a recognized disability, those will open before the class time, as like the quizzes normally do. Other questions about the exam? So the midterm, it's going to be the same material you guys have been seeing on the worksheets and the quizzes. Some of the questions will look very similar to what you've seen before, and some of them will be slightly new, especially, the essay format, I guess, will resemble the worksheets more than the quizzes. So you've had practice at both types, so that's good. And yeah. Okay, well, if there's no other questions right now about the quiz, then let's do this lecture on human sound localization. Okay, so you guys can see a big PowerPoint, right? Presentation to make sure we're all seeing what we're supposed to see. Okay, so basically the point of these kind of quiz or midterm week lectures is to relate some of the material that we've been hearing in the animal world to ourselves and to humans. And there's a ton of stuff known out there now about humans. It's not as, the techniques are much more limited for ethical reasons. And so, I would just say it's more difficult to study this stuff in people. But we've learned a lot, and I'll just present just a couple of papers and stories that I picked out of the mass that's available out there. So people use some of the same cues as animals, as I've kind of referred to throughout the lectures. For azimuth, for locating things in kind of horizontal space, we use interoral timing difference and interoral level differences. And interestingly, ILD turns out to be the more potent, or it's kind of weighted heavier in how humans localize sound as compared to ITD. So both of them are important. They both contribute to increasing the accuracy of sound localization. But in humans, ILD is the dominant cue. For elevation, we use spectral notches from the pinna, similar to what we saw in the bat. And so a side question there is why not ILD like the owl? And of course, that's related to our morphology, which is very, what do you call it? Symmetrical. I was trying to say synchronous, like that's wrong. It's not synchronous, symmetrical, where both ears are oriented more or less the same way. There's going to be small kind of developmental abnormalities and things, but nothing like in the owl where there's a, evolved, drastic difference in which way the ears point in order to be able to use ILD for elevation. So We use the spectral notches, in other words, the frequency aberrations produced by the pinna on the ear in order to determine elevation. And I think I mentioned before, a fun experiment that we would have done in class if we were together is to put clay in your ear, even if it's just on the outside, you know, so it's not blocking sound to come into your ear, but it's disrupting the normal shape of the pinna, the external ear. And if you close your eyes, it's very difficult to tell the elevation of a sound. You can still tell the azimuth very well, but if you're directly in front or back, it becomes difficult. And it becomes difficult to tell if it's above or below you. So it's kind of a fun experiment to do in class. So here's an example of an unplugged, so this is if you essentially put a speaker inside the ear and you map the frequencies that are coming into the ear, you get a different intensity of different frequencies that change depending on the pinna shape. So in the lower panel, it's an example of a plugged ear that again allows the sound in, but it just changes how the sound is manipulated as it enters the ear. And what they showed too is that these responses can change across time. So these people who wore these modifications in the plugs in their ears were able to adjust over time. So the response gain here is essentially just like almost like an accuracy measure. So azimuth was not really disrupted by the implants. It stayed as, you know, more or less constant, but the elevation response started out poor and then increased in accuracy over time, and essentially demonstrating that humans also have the ability to exhibit synaptic plasticity, assuming this is synaptic plasticity, but plasticity in our mapping of sound cues onto space maps. So people got better at locating sounds over time, but basically what the neurons had to do was learn the new spectral notches that are coming off of the implant instead of your normal ear. And that took, they still didn't return back to normal, but they got a lot better over, 30 days or so. So that's pretty cool. So in human sound processing, well, in any sound processing, errors can occur. And the sound localization system is able to weight the cues that it uses to localize sounds in space based on what it's learned is the cue reliability in a given context. So an example here is if you plug one ear, the system will actually learn to switch from using ITD and ILD to using spectral cues available from the unplugged ear. So essentially it changes the weight that it assigns to a particular cue from the sound in order to get the best information that it can. And that of course requires learning. It requires trial and error. And, but what's cool is that the system can learn, that our sound localization processes can shift and adjust to changing conditions. Another thing that's very human, and actually is true for a lot of vertebrates, is that we weigh visual cues really highly when or if visual feedback is available. And one example of this in kind of real life is the ventriloquism effect, where if you have a ventriloquist who has a puppet and they're using their throat, obviously, their vocal cords to make sounds for this puppet, but we actually perceive it, the audience perceives it as coming from the puppet because the puppet has the mouth that's moving. And obviously the better the ventriloquist, the more they're able to pull off this illusion by not giving any signs in their throat or their mouth that they're making the sounds. That creates a better illusion. And this has been demonstrated experimentally that we actually do shift our sound localization our sound localization towards a visual stimulus if it's there. So here's an example of an experiment where basically people were asked to, they were looking straight ahead, and they were asked to fix their eyes at the dot on the left-hand side. So it's a visual fixation. And then they played a tone that's slightly below that dot. And then they pause, and then they ask you to fixate again, and then they'll test it. And what they found is that with this kind of a training, this visual fixation training, you can actually start to bias where people localize a sound. So they'll localize the sound towards the visual stimulus. And even though the sound is always coming from the same place, if you move the visual stimulus, they'll suddenly perceive that the sound has shifted because they're linking the sound to the visual stimulus. And that's largely because we bias visual stimulus so much. Here's another example of plasticity. So on the left-hand side is a bunch of trials from somebody who was locating a sound's azimuth. And so that it was essentially highly accurate, very repeatable. And then they put compression lenses on. And I tried really hard to find like a visual example of what they would be seeing. But essentially it compresses, I think, the elevation, so like what you see in your field of view, by a half. So everything's compressed this way, and they wear these lenses, and then they have an assistant who goes around with them during the day, because obviously it's dangerous to have your visual system messed with like that. And then they measured them kind of pre-lenses and then post-lenses, and then they took them off and measured them again over time. And what this figure shows is that in the auditory cortex, the neurons change their firing patterns across time. And so during the experiment on A there, that's essentially mapping the degree of change. So the darker the blue, the more it's changed, and in that direction anyway. And so you can see during that adaptation phase, those 3 days of wearing the compression lenses, there was a lot of change. And then in the recovery phase, there was the opposite change. So the heat map changes from blue to red when it's the action potentials are changing in the opposite direction. And so essentially all this showed is that the activity patterns changed a lot in very particular areas. And so the other thing this map is showing, let me see if I can, yeah. So you can see these pretty strict lines here in these heat maps. And that's essentially the area of the visual field that was impacted by the lenses. So you didn't have a lot of change. There was some change in this upper one that didn't have a lot of change outside of that range. Another thing that was interesting that I haven't read that much about is that, so we've been talking a lot about how sound localization is place coded. We've been talking about how, you have your cortex or whatever from anterior to posterior, and there might be like a frequency map on that, or there's a three-dimensional map of interoral timing differences and interoral level differences in all these brain structures. That suggests that a neuron that fires within that map is indicating a place in space. What this experiment revealed, or what they argued, and again, I can't understand the modeling they used. It was really complicated. But they determined that sound localization was probably rate coded instead of place coded. In other words, it doesn't necessarily matter which neuron fires, like its place in the brain structure. What matters is which neurons fire and which population of neurons fire and how frequently they fire. And so it's a different kind of coding that we maybe more often associate with like intensity of stimuli. But in this case, in human sound localization, apparently rate coding is important. Okay, and then this is, so I play music, and we'll see if after this, I brought my little backpacker guitar, so I might play you guys a song if I'm brave enough. But I'm always interested in the perception of music, and why do humans love music so much? Like, what is it about music that's so special? Because we know it is. It's a very special thing for humans. And one of the cool things that kind of relates it to language, and the importance of language in people, obviously. But this study compares how humans and macaques, so a monkey and a human, how their brains respond to either pitched sounds, which are essentially sounds that are harmonic. So our language is harmonic, to unpitched or noisy sounds. And so over here on this left hand in panel A, you can see, so harmonic tones have this, basically there's 3 different frequency harmonics in, or maybe 4, I can't tell because it's hidden, in say this yellow sound. So this is frequency on the x-axis now. And essentially it's showing that there's peaks in frequency here, 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 and here. And those are basically the harmonic tones that make up the overall sound. So they're showing a bunch of different tones here. And what they did is they either played a harmonic tone, or they matched the decibel level, the loudness, and the frequency range, but they gave noise that didn't, it essentially was composed of all of the frequencies in this range right here, not just peaked frequencies at different harmonic distances. I'm gonna play, and so essentially we had humans showing larger responses to harmonic tones than to the noise, and macaques showing the opposite. So these heat maps show the response to blue. Basically, blue here is responding better to noise than to the tones, and so over here, here's the blue. So macaques had some blue. They had no yellow or orange, which is when color coding for tones are preferred over noise. And in humans, there were lots of brain areas that had a better response to tones than to noise. So something very specific about those harmonic frequency combinations that trigger activity in the human brain, but don't trigger activity in the macaque brain. And this is showing actually just frequency maps. So this was showing kind of the tonotopic arrangement of the auditory cortex. We have high to low frequencies represented here. So the macaque and the human brain are both tonotopically arranged. In other words, there's arrangement in this brain region, but they respond very differently to whether or not those frequencies are pitched or noisy. And then, of course, you relate this back to human language and the importance of processing human language. And I just included a recording of a macaque here. Another interesting study found that macaques actually have, so it used to be thought that monkeys don't speak because they actually don't even have the ability to. Like, their vocal cords cannot create language. They can't create the frequency combinations that are required to make complex sounds like words. And a very cool experiment where after investigating the properties of the voice box in macaques, they used a computer to simulate whether or not you could form something that sounded like a human word from a macaque. And you could. It's really creepy. Actually, I think I can't remember if I put that in here. Hang on. First, I'm going to show you what a macaque sounds like, and why it might be the case that macaques don't care that much about pitched kind of tonal sounds. So here's this. that's a macaque talking. So they have very different and very noisy, actually, vocalizations. And it's very different than human vocalizations. So, oh, okay. So I actually don't remember what this video is. We're gonna start it, and then I might pause it to see.
One of the big things that sets humans apart from other primates is spoken language. And new tests on macaques show the divide is even smaller than we thought. If they had the brain power to use language, monkeys might be able to talk to us. Researchers put macaque monkeys in an MRI scanner and measured the way they move their vocal tract. They built a computer model of a macaque from the measurements and ran human speech through it. The phrase, "Will you marry me?" Okay, so it sounds like something out of a horror movie, but it's easy to hear the words in there. And that's big news for biology. We didn't think monkeys had the anatomy to produce human-like sounds in the first place. Of course, to a macaque, that...
Okay, so yeah, just that's obviously totally a side point, but you know, the evolution of human language is a pretty fascinating thing. And so playing off of that now, like, why do we love music so much? And so there's a lot of theories out there. One of them is that most vertebrate animals have very complex sound processing, which is highly likely linked to our complex languages. And the ability to analyze sound and to predict, importantly, how tones in music might change across time, that apparently links into the dopamine reward system, which through neurotransmitters gives us pleasure when our predictions turn out to be true. Or in an interesting turn, when they turn out not to be true. So songs that surprise you with a weird chord or something can sometimes be more rewarding than songs that are quite predictable in how they're going to change. So this is an example of studying essentially the neuroscience of music. And what they did was they recruited people who reported kind of frequently or easily getting like the chills, having basically a really strong emotional response to a musical segment in a song. And then they brought them into the lab and used fMRI to look at how their brain changed while they were listening to that song. And so they studied kind of the anticipation phase leading up to the point that normally in the song gives the listener chills, and then during the kind of emotional response. So what they found is that dopamine activity in this nucleus, which is the caudate nucleus, is higher in anticipation of a piece of music that causes an emotional response. So that's this kind of lighter purple line here in the caudate. The right caudate is this lighter line, and it's got higher activity in anticipation. And so you get kind of more dopamine release in anticipation in that region. And this caudate region here that's having this kind of high dopamine release, it's interesting because it's implicated in basically reward sequences for stimulus response associations and learning, so classical conditioning paradigms. And so you see that this is kind of, there's a high level of activity in anticipation of this musical piece, and then during the actual part that would give you the chills, usually it's a climax in the music too. Now you get a change in activity, and the nucleus accumbens, which is a reward center that's involved in, or it's oftentimes implicated in addictions, spikes its activity. And so there's clear links in the brain between, kind of reward pathways and music and musical events. So the anticipatory phase is induced by cues that signal a potentially pleasurable sequence of music is coming. And this kind of creates a sense of wanting. And then, so If you actually withhold or make unpredictable or change that closure from a listener, then it actually enhances the dopamine release. So this is what I mean when suddenly there's something unpredictable that you didn't expect, or you're made to wait longer. It's like that you essentially you're building the anticipation, and that enhances the dopamine release. And composers are really skilled at this. And I've actually really enjoyed listening to a bunch of music lately to listen for this, because you can hear it in songs. That, you know, where composers are manipulating emotional arousal by actually violating expectations of the listener. So, you know, usually you start on a particular chord in a song and then you go to different chords, and the listener actually expects that you'll return to that first chord. And the longer you wait to do it, the more sense of anticipation is built in the song. And there's apparently some composers who were famous for not giving resolution to the listener until the very end of a long song, which sounds like kind of exhausting to listen to. But you guys all know some composer or a composer who's incredibly skilled at this and has become very famous because he's so good at creating music that matches this, you know, first of all, matches the emotional context of the movie, but then also that creates a sense of anticipation. And so here's two examples for John Williams in the Jaws soundtrack and the Star Wars opening. So in the Jaws one, he uses mostly, you know, this is mostly like kind of a bass change, but it's a change in rate. But listen to like when the strings come in, everything is built to just like increase this kind of sense of anticipation and suspense. Waiting for it. Yep. Can't pause it apparently. So what I find very cool about listening to that after, you know, reading about this, you know, kind of neurobiology music is like, you know, you start that and then there's a really long pause for like a song, you know, or whatever, a score, where there nothing happens, and then all of a sudden then it happens again, and then he doesn't stick with that same rate, right? It changes, and then they put in a couple of other sounds, and so it's constantly mixing up what you expect in order to build a sense of kind of unpredictability, and then all the other instruments come in that are all kind of, you know, building up the tension. The Star Wars theme, you know, does something similar. It's different. It's not as suspenseful, right? But it's like building emotion. So we'll listen to that one too. Those horns. So if the sound cuts off right there, you're going to be left very unfulfilled. But that resolution is the dun 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 dun. You know, where it just like brings everything back home. So anyway, you can see. So there's actually some very cool books on the neurobiology of music. It'd be a fun course actually to do neurobiology of music. But I really like connecting what you feel and what you know experience when you listen to music to understanding a little bit about, you know, the neurobiology behind your own response. It's pretty cool. And then as a songwriter, I don't, you know, I'm not a good songwriter, but I like to do it, and just learning about what makes a good song and how that actually has a basis in our own biology is pretty cool. So yeah, so now's the moment, I guess, where I'll share a song with you guys. I'm gonna end that show. So yeah, I'm gonna stop the recording. We don't need to have this recorded.